Okay, so started recording, and today we're going to talk about interpolation, which I realize sometimes it's been taught, it's been inconsistently taught as part of the lower division GIS course. It is something that we had all agreed to teach in this course, but that didn't always turn out. So if you had a course like this, there might be some repeat information. But we are going to talk about geostatistical interpolation, as well as, not on this slide, but we're going to talk a little bit about density, which is related to interpolation. We'll talk about that first, actually. Today's lab, although I think this is one of the more maybe complicated topics, I think that today, in my opinion, today's lab is a little more straightforward, like easy to get done, than previous labs. So it's okay. I mean, if Corey was going to miss one, it's a good time to not be there. Let's get on to what we're going to talk about. There are a number of slides. If you look at I did update the syllabus. If you look at the updated syllabus, the thing that I did in order to, because I said, basically, the week of Thanksgiving, we don't meet because we're a Wednesday class, right? The week before Thanksgiving now, I'm going to be in the Caribbean doing work. So we don't meet either of those 2 weeks. So in order to account for that, I had to compress. Not really. This lecture is pretty long. So what I did was just keep it one lecture, whereas I planned to break it out into 2 lectures. If we don't get to everything, then we'll try to squeeze it in another week. But I think we can do it. So we're going to talk about 2 different types of interpolation. Our traditional, what's often referred to as deterministic interpolation. We've used that term before. So basically, there's a mathematic formula that gives a single answer for a single set of points. That's what deterministic interpolation does. And one example is IDW, and we're going to talk about how IDW is calculated today. We're going to talk about different categories of interpolation. And then we have quite a few slides on geostatistical interpolation, or kriging, which has applications beyond interpolation, but it's definitely important for this topic. So sometimes we refer to a surface that gets created from a group of points, a statistical surface. So we have a sample of that surface. So one way to think about, I don't know if you've taken a statistics course, but one way to think about the process of creating a surface from a number of points is to basically infer values on a surface from a sample of that surface. So it really is a statistical operation where we don't know the values everywhere. That's our goal, is to create a value at any given location based on knowing the values, the z value, the a value, at a number of xy locations. So this is often done for topographic elevation. So building on the last lecture, this is often how elevation surfaces are created, because we don't know the elevation everywhere, but sometimes we know the elevation some places. But any measurable attribute, I say numerically, but actually we're going to cover non-numerical attributes as well, that vary across space, like temperature and population density, can be interpolated. We can actually make statistical surfaces of even non-numerical data Well, it actually has to be numerical, but it doesn't have to be interval ratio. Could be points. So the end goal, and the reason why this is discussed in this class, is that the end goal is to create a raster grid. So I said a statistical surface allows us to come up with a formula for finding the value of a surface at any location based on a number of sampled locations. So we know the values at these locations. What's the value here? Well, in practice, what's often done is that we find the location at regularly spaced intervals, and we refer to that as a raster grid. So the input is usually a bunch of points where we know the values at those locations. Those are known values, whether they're weather stations or they were LiDAR points from a remote sensing instrument, or if they were collecting pollution at various places. I think we sampled them in the water. Whatever. Those places where we know the values are the inputs. And the output, just like a lot of the things we've talked about here, is the we're going to call it the interpolated value, but another way to think of it is the output of that function, that process, at the center of each cell. There are other ways, though, to come up with a surface. One of them is a triangular irregular network, which we talked about. That basically just creates a plane in between, a plane, not an airplane, but a plane in between the known points. Contours are usually derived from one of these two above sets, though. So contours or isorhythms are lines where the value on that surface is equal. A lattice is like a more general term for a grid where the spacing might be regular or irregular. It could be triangulated, but it could be more of a pattern, hexagon, whatever, something that tessellates. We're going to focus on raster today. So I did mention that there are two types of data that we can turn into surfaces. One is data that is not countable. That's another way to say basically data that is already conceptualized as a field. In geography, sometimes we refer to different variables as features and fields. So field means that variable exists everywhere, and it changes everywhere you go. Okay? Temperature doesn't change very quickly. Obviously, the temperature here is pretty similar to the temperature here. But as I traveled all the way to Minnesota, in general, the trend would be that the temperature got cooler and cooler as we traveled northward. So that's one type of data. And to do this, anything that is conceptualized well as a field, we're going to use interpolation methods. So other data, though, is in punctiform. It's data that are composed of individuals whose distribution can be modeled as a field. Things like population density, whether that's animals or people or observations. We can. It's not really a field. In other words, anywhere you go, the population density of a particular location is either 1 or 0. There's either a person there or there's not a person there. But what we could do is come up with the average population density in every cell for the area surrounding it. In that case, it's kind of like doing a neighborhood operation, where the neighborhood becomes the area around, and we're coming up with the value for the cell inside of it. So we're going to talk about that one first. That exercise is called density estimation. Okay? So this slide has both on it. So this is spatial interpolation. We'll talk about that later. Density estimation creates a field from discrete objects, usually points, but technically we could also do it with lines. It doesn't really make a whole lot of sense to do it with polygons, so it's either lines or points, typically points. All right, so the field, so you could read the raster, the output raster. The output raster's value at any point is an estimate of the density of discrete objects at that point. So something like estimating a map of population density, individuals, those would be discrete objects. Even if we don't have those modeled as discrete objects, like we had census information down to the house level. Every house could be a dot, and we could have an attribute assigned for how many people lived in that house. And then we could plug it into the formulas that we'll talk about. So we can do it with points and lines, as I said. We want to calculate their density. Here's some examples. Density of population, density of disease, density of roads in an area. Let's say that we're trying to come up with a model for where we'd most likely see a certain species of animal. We could create a road density map that would perhaps be the opposite of the probability of seeing this animal, because it doesn't want to live near roads. When it does come near a road, it usually gets run over or something. That's kind of sad, but, all right, so how is this done? In the most basic form, this is how it's done. All right, we have our point data, and we take our point data and we overlay a raster to our point data. At first, the raster is completely empty. There's nothing in it. Then you have to determine a search radius. Okay? The search radius, kind of like a neighborhood operation, goes cell by cell and counts how many dots or how many points fall within that cell. If it was lines, it would be doing the same thing. How many lines, how many individual lines are in this cell? So in this case, there are 2. And so the center of that cell gets a value 2. And when we move to the next one, we're still going to get 2. But finally, when we move to the center of this cell here, there would be 3 in the search radius. So it would get a value of 3. So it would create a density surface. And that's the most basic way that it's done. There's a tool in ArcGIS. I should have opened up ArcGIS already. There's a tool in ArcGIS that does this. We're not going to do this in the lab. It's pretty basic. But it's called point density. So I'm not going to do that right now. I'll wait for ArcGIS to warm up and do it later. So go back to the lecture. Maybe. Okay, there we go. Okay, yeah, I like this view better. So you can see this one has a value of 6. Why? It's because it has about 6 other cells. All right, it's nice to know the ArcGIS is up now. 6 other cells. 6 other points. 1, 2, 3, 4, 5, 6 fall in the middle of that one. Okay. So you could do it for trees, which is the example here. You could do this for people. You could do it for animals. Lots of things. All right. The output of that, well, here, now the ArcGIS is warmed up since it took so long to talk, I will show you the output of that. So under Lab 8, I have some data, some soil pollution data. And this is data that we're actually going to use for interpolation. But just imagine that this soil pollution data represents people or some other countable data. It's actually not in It's not in a shapefile yet, so I've got to create the XY. You have to do this in the lab anyway, so I'll go ahead and explain it. It's got northing and easting values. Which one is X and which one's Y? Right, exactly. Easting is and northing is Y, because as we go north-south on a Cartesian coordinate, we're going up and down. But it doesn't really matter what coordinate system it's in. So I'm going to say OK, and those are the points. These are the points we're going to use for the lab. But imagine that these represented something countable. These are people or trees, whatnot, whatever they are, and we want to make a tree density map. Under Spatial Analyst, there's a toolbox called Density, and we're going to do point density and choose the input features as the soil pollution events. And the population field is the field that you would use to say how many things were at that location. So if it's population, if there was a field that represented the amount of people that live in a particular house, you could choose that field. Otherwise, it just counts every point as one. But if you change this, it could count a point as 2 or 3 or 4, whatever you had to face up. So I'm going to leave that empty. This is the output cell size, and this finally here is the output radius. The output radius is the circle that it will search for. So I'm going to leave those defaults the way they are. I kind of get bothered by cell sizes. What's that?
Is the units of the radius depend on what your projection is?
Exactly. So since I said unknown coordinates, they're in unknown coordinates, but they're still real because there's still a distance between 2 points. I just didn't tell it what unit they're in. So okay. It's 66.73333 unknown units. I could have said they were in meters, which I do think they are in meters. Then it would be meters. Right. There are some tools that actually care if you put the units in. This isn't one of them. So, okay, so I'm going to say OK. And when that runs, what it's going to do is create a map. It's going to run pretty quickly of the point density. There we go. So you can see, everywhere where there's just one circle now has a value of 1. In these overlapping areas, there's a value of 2, where 2 polygons, 2 of these circles overlap. In some places, there's a little teeny one there, kind of bigger ones here. There are 3 that overlap. I guess I should be pointing that out in here too. So there are 3 that overlap, and so you get a value of 3. All right, so that's point density. Now, these numbers don't look like 1s, 2s, and 3s. Well, by default, ArcGIS divides it by the area. So it's the amount of dots per area. And did I decide to go to 8 or 5 cell size? 5. Okay, so it's 5 times 5 divided by the count is that number. And you could find that out in the description here, but that's what it does. So you could multiply it by the cell size to get 1s, 2s, and 3s. Okay. Some people said, well, this is great, but it doesn't really give the impression that I want it to give because it's just too discrete. Really, I want kind of a map that shows me the dense areas and tapers off as I get out of the dense areas. You've seen population density maps, right? They don't look like this. They have circles around each of the points. That's not the way they look, right? They look like they taper off slowly. And so there's an alternative method for density estimation using kernels. And really, it's the same type of kernel that we've talked about before, but it's creating a specific kernel that tapers off from the center of the point. So instead of assigning a value of 1, it's assigning an area of 1 based on a normal distribution about a point. So it's kind of like the area under this point is 1, and then all the areas are added up. Okay, so each point is replaced by kind of like, one way to think about it is a pile of sand. It's a consistent shape, it's a constant shape. It looks like a bell-shaped curve, but in 3 dimensions. It's rotated about an axis. So it looks like a haystack or a pile of sand, whatever you want to call it. So if there are 2 that overlap, then they're added together. Their value is added together. So you get a nice, smooth sand pile. Sometimes it has multiple peaks and ridges and valleys, and that's the result there. Now, by default, ArcGIS and most other software packages, when they're calculating this, the shape of the kernel depends on the distance parameters. So increasing the value, that circle that it's looking, will create a more flat kernel, and decreasing the circle radius will create more of a peaked kernel. So you get a narrow kernel or a peaked kernel because the area under the curve is what's constant. So you're gonna have to have a more peaked one to get more area under a smaller curve. So here's a kernel density function for some points. The points should be on here too, but they're not. This is a narrow kernel. And this is a wide kernel. And the wide kernel is more smooth, less bumpy, but it's less specific. So it's something that's often, it's actually done a lot for cartographic effect. Anybody know what we call? Seen these kind of maps before. What do we call these kind of maps? There's one term for it that gets used a lot. Heat maps, right? Anybody use that term, heat maps? Maybe it doesn't get used in Brazil. Thermal, yeah. Well, you could look from this map. It kind of looks as if it's trying to show you heat, right? Like this one, if this area was burning out, heat has that ability to dissipate. So it's not really showing heat, but it's showing population here as heat. That kind of makes sense because if you were in one of these areas, it would probably feel more dense, like you'd feel that there's more people around you than if you were out here. Okay? So it's not a real thing, like you can't measure population, like I was saying, you can't measure population at a given point, but it's useful in telling people, in communicating to people what's there. So it's used a lot as a cartographic effect to communicate an idea that is an abstract idea. It's not real. Well, it is real, but it's not something that you can actually see all the time. You just notice it. There's more people around here. Well, that's the impression you get there. What's that? Yeah. And there's more people around here. And anyway, so because it's a cartographic effect, you tell a different story in each of these maps. So it's often something that you experiment with. You do it a few times. And if you're going to use it in analysis, you need to check that whatever you're actually trying to analyze holds up to that thing. Because it can be useful for that, because it's a surrogate for the amount of people per area around you. It's just you're changing that area around you. That's what the difference between these two. You're looking at 1,000 feet out versus 200 feet out. Maybe a different reason for doing that. So here's another example. But lots of times, when you make a map like this, a heat map, for communicating, for visual purposes, you try to get the radius out so that it starts to kind of be a little fuzzy. And so when you have a lot of points that just still appear as circles, it's usually helpful to make it go out a little bit further. So here's the kernel radius of 150 kilometers. If we did that to our data here, we could do that with the soil pollution events. I'm going to change this back to 5. You notice now that the search radius is optional. See how it says optional? Let me get that. If you leave the search radius empty, it's going to calculate a search radius that's based on the standard distance, the average distance that points are away from the center. And it's just basically a formula that somebody came up with that they thought would make the best looking kernel density. And it doesn't work for every data set. If you have data where you have lots of points far away and a few close together, the standard distance is going to be the same as if you had points that were kind of averagely spaced. It doesn't work for every data set, but it's a good starting point. So you can put your own search radius in, but this tool allows you to say, okay, well, use the best search radius the search radius that people have decided is a good one. Kind of like with Hillshade. If you're actually trying to do some analysis, you should probably pick your own search radius. If you're trying to make it look good cartographically, this is a good starting point. Go ahead. Yeah. There are tools. We actually used them in the 217 class. There are tools for calculating standard distance. So you can calculate standard distance without that point manually, and then put that value in there, what the standard distance is. Okay, so I'm just going to say okay here. It takes a few more seconds to run. Actually, it seemed like it took less. But you see, maybe it just hasn't warmed up yet. But you see how it creates these more smooth. It gives you an idea of where, if these represented people, where if you were walking down here, you'd be walking amongst more people than, let's say, if you were walking up here. Whereas it might be a little bit hard to tell by just looking at the points. But this is oftentimes easier to use to communicate. Not that one. I meant to turn this one off. Because oftentimes you actually turn this layer off to show the values. So that's a heat map or density estimation. All right. So what's the difference between these two maps? Well, I don't expect you to guess or anything, but do these maps look different besides the color? On the right over here has a larger kernel. Well, this one actually isn't even a density map. So this one is where we're going. This one is where we just went. So this map, instead of counting the number of observances, is just looking at the values of the points and creating a smooth surface. So this is interpolation, and this is kernel density estimation, or just density estimation sometimes. Okay. All right, so now that's where we're going. Interpolating a surface from point data. So one thing I want to drive home here is that we use the term interpolation because the idea is that we're estimating the attribute values of locations that are within the range of available data. Extrapolation is another term that gets used a lot. They say, well, how did you extrapolate that? People say that. That's looking at values of locations outside the range of available data. Now, ArcGIS and most other software packages will allow you to interpolate values outside of this range. So in other words, if I was to say, what's the elevation here? That's technically extrapolation, although ArcGIS will let you do it. It's not as reliable as this, which is interpolation. What's the value of elevation at that point? That's interpolation. Extrapolation, like this, is finding out the location of a point here. So it's really risky to make a judgment about what the elevation or what the surface is of any sampled surface outside of these values. So that's an important thing. Okay, so let's talk about different types of interpolation. And again, this is where it may be a bit of a review to everybody, but we're actually going to get into the mechanics. We're going to calculate some of these. One of the first types of interpolation is just a simple linear interpolation. And this is pretty much what a tin is doing. What a tin is doing, but a tin does this in 3 dimensions. So it would be planar interpolation. But I just showed you this to help you kind of understand. We just basically draw a line between each point. We refer to that as linear interpolation. And here's the math for if this was a line, but in space, we're often talking about a surface. But there's still just plain old Cartesian math that gets used to find any point on a plane. C is supposed to be estimated. So any point on this line, thanks. So A and B are known points. C is an estimated location on this surface. All right. Lots of interpolation algorithms are nonlinear. They often result in more realistic interpolation, but they're complex. So they're bending through the points, okay, based on a trend or something. There's not a specific single nonlinear interpolation. This is a category of interpolators that we'll talk about today. Another category of interpolators are exact versus inexact interpolators. Exact interpolators pass through all the original data points. So in other words, if there is a point at the center of any cell, an exact interpolator will make the value of that cell, its math will work out, so that the value of that cell is the same as the value of the point at that location, if they're exactly in the same spot. That's what an exact interpolator does. An inexact interpolator, it doesn't pass through all the original points. It follows a trend usually. All right. Some interpolators, a few, that are useful for some purposes, use all of the sampled locations. Every sampled location, usually these are like trend surfaces, we find all the sampled locations and we fit a trend surface through the data. Those interpolators are referred to as global interpolators. A local interpolator only looks at one or a neighborhood of sample data at the same time. So it could just look at 1, 2, 3. It's a neighborhood that you define, just like we defined our neighborhoods in previous portions of the course. So that's local interpolation, okay? Looking only at neighboring points. We can define the neighboring points later, but in general, just like with a neighborhood operation, as we look at more and more points simultaneously, the surface gets smoother and smoother. Okay? right? So we talked about this a little bit at the beginning. Why? Well, we just simply can't measure every location. We don't have enough time or money, besides the fact that it could just be impossible to go everywhere. And so if we have missing data or unsuitable data, how do we fill in that data? That's interpolation. We're going to talk mostly about spatial interpolation, but we could also interpolate data through time, temporal interpolation. Interpolation can be done, and there have been research papers on this, looking at this, when you change cell size rather than just simply resampling. Resampling just means to take, every fifth cell or every eighth cell or every, when you go up and down. Okay. All right. So getting back to that question that was tough on the test, we're going to talk about spatial autocorrelation. So Waldo Tobler was a scientist. He came up with what we now refer to as the first law of geography. In space, everything's related to everything else, but close things are more closely related. And in numerical terms, in other words, if we want to quantify this, we refer to that as spatial autocorrelation. And spatial autocorrelation is measured the degree to which near and distant things are related. And if you think about it, they can be related in different ways. So typically, there's been other scientists, Moran, that have actually looked into quantifying this. Typically, we refer to this as negative spatial autocorrelation. You might think that that near values aren't related. Well, they are related. They're just oppositely related. Every other cell is different. It's perfect negative spatial autocorrelation. As we go to the next cell, we get the opposite value, or as long as we can predict it, up and down, up and down. That's negative spatial autocorrelation. Zero spatial autocorrelation exists when the values truly are random. So like with elevation and temperature and precipitation, that doesn't happen. Nearby values are always related. They change in the degree to which they're related, like if we have a big cliff that just drops off. But there's still a trend even with that. As you travel one direction, they're all dropping off. Travel another direction, they're all staying constant except for that jump. So there's still some spatial autocorrelation there. If it was all truly random, we don't live in an area where that's really the case. But there are surfaces like this, but most things that exist in nature have some degree of these. All right, positive spatial autocorrelation is when they're all related. Nearby values are related to each other. This shows like on and off. But even if this was a slowly or quickly changing trend, like in other words, if it started down here and slowly or even quickly increased to the other side, there'd be lots of positive spatial autocorrelation because the values close together are related to each other. They're slowly changing or they're quickly changing. Either way, they're changing at a constant rate. It's more about the constant rate. Similarity in attributes of things that are close. Yeah, so right. Like overall, this has a high positive spatial autocorrelation. But if our grid only contains these two cells, then in one direction, there would be negative autocorrelation in the other direction. Well, if it only contained these cells, in this direction, it would be always the same. So it would be positive spatial autocorrelation. In this direction, it would be negative autocorrelation. It would be always different. So you can have autocorrelation measured in a certain direction, and you can also just measure it for a circle. Anyway. So here are some other examples. Just an extreme negative spatial autocorrelation, extreme positive, and then basically extreme positive means that they're extremely clustered values. Spatial clustering is some spatial clustering would still be positive. Not much spatial clustering would be negative. No spatial clustering is independent. Yeah, so the independent example is truly random. Dispersed, there are some cells that are dispersed out. You see how there's a pattern in some places, but the pattern doesn't exist everywhere. It's more similar to this one. So it goes from this one to this one to this one to this one to this one. This one would be extreme negative. That one would be a little bit negative. This one would be close to 0. This one would be a little bit positive, and that one would be more positive. But you notice this doesn't go all the way to 1. It's really hard to have an ideal. It's really hard to show an ideal positive because there's always, like you said, there's that interface. I don't know. I mean, it would be interesting to see which one would get a better value. But yeah, this is just showing ones and zeros. So in this, that's the best you can get, and it's still not quite there. But if you had a gradient, that might be able to get a little bit higher. Okay, so this is probably the most important message on this slide. We're going to go through a lot of interpolation methods. There are many different methods. They within the methods themselves, there are lots of variables that you can change, or at least a few variables you can change in each case. Okay? They all produce different results. No single method has been shown to be more accurate in every application. So if you're interpolating temperature in North America, it might be different. Well, it is going to be different than interpolating elevation in some other place. So there's the application, there's the location that you're trying to do it. It has a lot more to do with how much is changing. And the best way to judge accuracy is by withholding some of the sample points from the interpolator. So if we're going to do an interpolation, you withhold a subset, maybe 10% of the points, and then do the interpolation and figure out how far off those points are on average. Because if you have 10, you can come up with an average. Sometimes in statistics, we call that a residual. You can calculate the average residual value. And remember that you can't just use the positive, you can't just use the values because some are going to be above and some are going to be below the surface. So in other words, let's say you only withheld 2, and one was positive 3 and one was negative 3 from the actual surface, then you could say I had 0 error. They were all on the surface. Now, that's not what that means. Typically, the statistic that's used is RMSE, the root mean squared error, which is used a lot in statistics and in GIS. So it's basically you take all the errors, you square them so that then they're all positive. You add them all up, find the mean by dividing them by the total number, and then take the square root. We're gonna actually do that in the lab today. Okay. So we talked about how it's usually used for raster data. The contour lines are usually a byproduct, the second step. But there are some software packages that create vector lines straight as the result of these interpolation algorithms. We're going to focus on this raster surface. So here are some elevation contours based on values. Okay. All right, so the first one we're going to talk about is almost like the bridge between the punctiform data that we talked about before, just using the points, and what we're talking about now. It's discrete, but it's discrete in a different way. These and polygons, sometimes it's referred to as nearest neighbor. All it does is every raster cell gets the value to its closest neighbor. So if we're talking about elevation, every raster cell finds the closest known elevation point and takes that value. Or if it's temperature, it finds the closest temperature value. It's conceptually very simple. It usually creates a kind of maybe an ugly or a disjointed surface, one could say. The boundaries are often odd shaped. They look like polygons. They're technically called decent polygons. But it is pretty easy. And the accuracy is not necessarily low. Sometimes, like people have shown, like with temperature, if your points are already pretty dense and we're talking about temperature, sometimes this can be as effective as any other interpolation method because temperature changes rather slowly through space. Yeah, on any of these you can put a threshold on the distance, but then beyond the maximum distance you wouldn't have a value, which I mean may or may not be acceptable. So one way to think of it, I'm going to go through this a little bit faster. This is pretty easy. But if you have questions, just let me know. Basically, if these represent the sample points, halfway between all the sample points you could draw a line, and that's the polygon that it's going to create. It's going to look like this. So all those raster cells that have a center inside of these polygons, all the rasters that have a cell within that polygon are going to have the same value. In this case, it's going to be 300. So any raster cell that the center falls in that polygon has a value of 300. Okay, pretty straightforward. Here it is with the data we're going to use today for the lab. Here's all those points. Here are the Thiessen zones for this. There's a bunch of samples of different dissolved materials is what this is. This data actually, so the reading for today came from the book, one of the books we used to use for this course, and the data that was provided in that book. Okay. All right. So you'll notice that the figures from the from the text coincide. All right, so that's Thiessen polygons, pretty straightforward, easy to understand. The next one is also, I think, pretty straightforward for anybody that's taken a statistics course, except for now, instead of creating a trend from data, we're going to take a trend from all the data in 3 dimensions. It's a 3-dimensional trend surface. So this is a global method. In other words, it accounts for all the points at the same time. It's inexact, meaning that it tries to fit through the points using a line of best fit. Doesn't mean that it won't fit through some of the points, but it doesn't try to fit through all the points. It tries to find the surface that minimizes the residuals, the distance between the known value and the value on the surface. It can be linear or nonlinear. If it's linear, the residuals are going to be larger because it's basically just trying to fit a flat plane through all the surface. It's basically a multiple regression in 3 dimensions rather than just in 2 dimensions. So here's a review. In 2 dimensions, it would look like this. Okay, we're trying to fit this line of best fit, the plane of best fit. If we tried to fit an arc through here, a second order polynomial, it would probably go like this. would go through like, oh, here, I should show that. It would go through like this. It would be arcing through because it would minimize that distance. They call this, sometimes they call this least squared regression because it's trying to minimize, in other words, make the number as low as possible, the residuals between the surface value and the individual data points. So in 3 dimensions, it looks kind of like this, where we're trying to get the distance, we're trying to minimize all of these residuals. Now we don't actually do this math, but this is what it's doing. Okay? The computer does this math. It creates a trend surface, a linear trend surface. If it was a second order polynomial, like I said, it would look like that. So this is the output of a trend surface. The reason why I'm using contours is a little bit easier to see. So this is a trend surface. This is the original surface. Who knows what the original surface looks like? But the trend surface is always smoother. This is a second order trend surface. Actually, this is a third order trend surface, meaning that it bends in both directions. It bends in 2 directions. So it's a plane that bends in 2 directions. Okay, what else do I want to say about that? This is often used for things like temperature and precipitation that's changing slowly. And another thing this gets used for a lot is to come up with a trend surface that can be compared to a more detailed surface to see what areas are the most off trend, to see where the values are the most different. So if let's say we had a surface like So let's say we had a surface that represented air pollution. And we used some traditional interpolator to come up with air pollution. And we verified that it was doing a really good job at making an air pollution map. Okay, so think of that in your mind. It looks kind of like a heat map, but it's a little different. It's showing the areas that have higher air pollution, lower air pollution as an actual surface. The next thing we could do is create a trend surface of air pollution, because it may be that there are certain areas that should have lots more pollution because they're up high in the mountains, in a mountain valley, or right along the edge of a coastline like Los Angeles. So we come up with a trend surface, and the trend surface will show the general trend of the way the pollution looks, and we subtract the general trend from the original, from the actual, it's still an interpolated surface, but it's the one that's more accurate. And oftentimes this is referred to as an anomaly, creating an anomaly map. So we see things that are different from the trend rather than just seeing the raw values. And so that gets used a lot in science. So creating a trend surface, it's kind of like finding the average value. So I could, like with grade, let's say, we could report everybody's grade as a percentage of questions they got right. But if I wanted to, I could also report your grade as a deviation from normal, from what the normal grade was. So this is one way to create the average, since we're talking about it in space, the average value over space, and subtracting that value off will give us the anomalies, the differences from normal condition. So this is a simple first order trend surface. So it doesn't bend at all. So it just shows that as we travel away from the water in general, we get less of this, whatever, I forget which one's B, zinc. We get less of it in the samples as we travel away from the water. That is actually something that might be useful. Look at a first order, it kind of removes the noise, and you get to see what's the general pattern. The general pattern is as we move away from water. Maybe that's something that's significant, maybe it's not, but it's something that definitely looks less noisy than this, or what some of the ones we'll see in the future. So here's the second order, meaning that it has one bend in it. One bend in each direction. You can see it bending this way and bending this way. And you can see that it actually still has that same trend we noticed, but it also tends to get higher once we get further away. And then finally, the third order surface. Okay, so now it's bending twice in both directions. You can see this peak over here down, and this other peak over here. And then fourth order. And as we get more and more higher orders, it's bending more and more, so it's fitting through the points closer and closer to the points themselves, but it'll never quite reach all those values. All right, splines are basically it's a local method. You can force it to be an exact interpolator, or you can tell it there's an option, checkbox, don't want it to be exact interpolator. They're nonlinear, and they're actually like the trend surface that we just created, except for the trend surfaces changes. Everywhere it's only using a local set of points to create a trend surface. And this was derived from the use of flexible rulers for drafting, which are called splines. And so we're fitting a bunch of flexible rulers. It's a piecewise polynomial function. So just like we talked about the global trends, this is the same kind of math, but we're just doing this on a piecewise basis. They typically produce a pretty smooth surface. So it's often used a lot for a cartographically pleasing output. The minimized curvature will ensure, basically you can specify how rigid these splines will be. Right? You can adjust the tension of the spline. It's kind of like fitting a metal sheet through a bunch of points. This is the way it would be in one dimension. This is a horrible drawing, but I tried. Okay, here's ESRI's attempt, a little bit better. This comes from the help page. You can see these are the points, and we're fitting a metal sheet, a flexible metal sheet, or maybe even today. When we talked, these are originally metal rulers, but today we could talk about some polymer that would be better. So you can see how it produces these smooth surfaces. Okay, they're often thought of as being visually pleasing. Here's a regularized spline, the 12 nearest points. So right now, for the next few interpolators, we're going to talk about comparing the 12 nearest points to the 6 nearest points. And when we consider less points, we get a less smooth surface. It's harder to see in these, but in fact, between these two, you can't really tell. I might have had those reversed, who knows? But between 3 and 6, you can see it. Okay, it's less smooth. You can see these little guys popping up, creating more variability. So as you use less points or consider a smaller area, you get a less smooth data set. So this is regularized, and this is tension. In other words, the tension is the higher, the sheet isn't as flexible. So you can look at the difference between this one, and you can see how the sheet is more flexible. It's bending more here than it is here. All right. We are going to still talk about measuring the accuracy of these things in this course, but we may not get to it today. But we're going to introduce the concept in the lab, because the question is, with I know probably some of you are thinking, with so many interpolation methods, how do we know which one we should use? And yeah, it's different for different things. You need to be able to make sure you take enough sample points in order to calculate it. All right, here's inverse distance weighting. This is an old, tried and true interpolation method. It's oftentimes the default interpolation method to compare other interpolation methods to. It's a local method. It is exact. It can be linear or nonlinear. There's actually an exponent that you can specify, and you can change that exponent. And if you make it higher than 1, it will be nonlinear. If you make it 1, it'll be linear. So the weight of a sample data value is inversely proportional to its distance from the estimated value. We're actually going to calculate this in the lab. Here's the formula, and maybe a formula with a few Greek letters is hard at first, but this is actually a fairly simple formula. So this is the value in the output raster cell, okay? And then this is the sum of basically the measurement of these points that are nearby. You define what it means to be nearby. So if there's 7 points, it's the sum of all those measured values, and there's a little bit of math involved there. And this is just a sum of the distance to those measured values. So that's why it's inverse distance. The distance is below. So we're going to weight these points by their inverse distance. So kind of like taking a test. If I weighted one test twice as much as another test, then I would call that a weighted grade. If I did an inverse weighted grade, I would divide, the weight, maybe 1 over the weight to get the inverse weight. But because that distance is on the bottom, it's going to create a point. So we'll walk through the math here in a second, but it's going to create values that are more weighted the lower the distance is. So this is the basic: find the neighboring sample points, then find the distance from each sample point to the target location, and then this math weights each sample point according to the inverse of its distance, and you find the average of the values. So if all the distances were equal, then this would simply be the average of the 3 nearest or the x nearest points. But because this is different, we're dividing by a number that's the inverse of the distance. And we'll walk through the math here in a second, but just to show you, here's the 6 nearest points, and here's the 12 nearest points. You can see that the 12 nearest points is smoother than the 6 nearest points. Okay, here's a few more examples. 12 nearest points versus, this is actually not nearest points. This is the power. And as you go up in power, it will be more smooth as well. See how that's more smooth than that? It's increasing that exponent. So this number right here, this R, it's increasing that value. So you're basically what you're doing is basically increasing the weights for faraway values more. If you left it at 1, then it would change. Then it would be linear. So here's IDW power and the interpolated value. It becomes more smooth. Also, one of the other things you can change with IDW is the search radius. You can say, I want to look at the nearest 3 points regardless, or the nearest 4 points, or the nearest 5 points. Or you could say, I only want to look at the points that are within 500 meters, and I want to look at all of them. So here's looking at 500 meters or 1,000 meters. And the 1,000 meters is more smooth. Okay, 500.
When you're saying smooth, you mean less detail?
That's definitely one way to look at it, yeah. There's the values change more slowly. Is how I'd define it. But it will smooth over, or if there's more detail in the original, it will make the changes between those less abrupt. Yeah. Yeah. So yes, you're increasing the autocorrelation the more you do that. Okay. Yeah. All right. So here's the math involved, and we're gonna do this as part of the lab. But let's just say we were considering the nearest 3 points, okay? Or that all 3 of these points fall within the search radius. And this is the center of a raster cell. That's what the red dot represents. The center of the raster cell. In this case, we've chosen the closest 3 neighbors, and our power is going to be 2, which is the default. That's the default power for IDW. Okay? These numbers here, 4, 3, and 2, represent the distances away from these values. And the numbers here, 160, 100, and 200, they represent the value of the surface that we're trying to create at that point. So they could represent temperature, they could represent precipitation. Those are the values we're trying to interpolate a surface for. So we would expect that the value at that red location would be somewhere between 200 and 100. I mean, we're doing interpolation, and we want to create a surface, and it's in between 3 points that have a value of 100, 160, and 200. Now, it is closest to the 200 value. It's the second closest to the 160 value. So, if you were to guess, you might think, the value is probably going to be, at least greater than 150. So we'll see in a second. But see how it's closer to these values than it is to those values? All right. So this math is only going to involve adding up 3 different values. There's 2 ways to think of this math. One way is easier for some people, and one way is easier. They're both the same, really, but you could basically add up the numbers first or second, and calculate the weights first or second. So one way to think about this is to look at the weights, right? The weights first, because that is the bottom part of the equation here. So calculating out the weights, we're going to get a value from the center of this cell up to A as 4. So the weight for this point is this number, 0.0642, because it is the distance squared, and it's the inverse of that distance. Likewise, with 3, it's the distance squared, it's the inverse of that distance. 2 squared, which is 4. The inverse of 1 over 4 is 0.25. This is probably the easiest one to do in your head. Okay? Now, the thing is that our weights always have to add up to 1. Okay? So the next step is there's a few ways to do this, but the easiest way, or not I shouldn't say the easiest way. The other way is easiest for some people, but one way to do this is to add up all of the weights. Once you add up all the weights, you can then divide each of the individual weights by the total, and you'll get a normalized weight value. So in other words, what's going to happen is that A is going to be weighted 0.15. We're going to take 0.15 of 100. We're going to take what's that? Oh, no problem. it's going to take, we're going to take 0.26 of 160 and 0.59 of 200. So you see how we're going to take more of this value, not even half of this value, and then only a little bit of this value, because it's the furthest away. So the next step is to multiply everything by the adjusted weight. So 10 times 0.15 is 15. 160 times 0.26 is 42. 200 times 0.59 is 118. And then we simply add those numbers together, and we get our value, 175. See, it's what we expected. It's a value well over 150. It's a lot closer to 200. That's how IDW works. So another way to think about it is that we might, if you go back to the test analogy, this might have been individual scores, but what we're doing is saying that we're going to weight this score more heavily. Maybe it was a more important test. We're just saying it's more important when it's closer, instead of it's more important because it was twice as long or it was the one at the end of the semester. And the way that we make it more important is we give it a bigger weight. But we can't weight distance, otherwise it would be all messed up. This one would get the highest point. So we need the inverse of the distance. If we did make all of these 1, it would be, 1 divided by 4. It'd be a linear interpolation, as if there was a plane between these 3 points. But increasing that number will change. And one of the questions on the lab will be you calculating these out by hand, okay? and seeing how it changes it, because it'll make that more apparent. All right, so another way to do this, that sometimes, I'm just going to explain this as another way to do it, that some people prefer, is to take the weight that is basically the smallest weight and divide everything by that, okay? And then multiply everything by those weights, add those up, and then divide by the sum of the weights. So 6.8 is the sum of the weights. I think the first way is better. I slipped and followed the best way, and I think it is. It's a little more straightforward, but this is a little bit more like this allows the weights to be a little bit more straightforward in terms of what they mean. Hey, this is weighted 4 times what this is weighted. This is weighted 1.8 times what that's weighted. So sometimes people think, I think it's a valid argument. Sometimes people would think that those values were more easily to interpret than these values. Although I can think of, those are basically only adding up to 1. So it makes sense to me. Instead of adding up to 1, you're actually seeing them as multiples of the lowest weight, and so they both have a practical reason. This one involves one more step. You have to do one more divisor at the end, so it is slightly longer. All right. This is yet another way where you could just take the weights and multiply them directly, and then what are you adding? Yeah, you're just dividing by the total weights. So this one actually doesn't involve an extra step, but it doesn't allow you to see the weights as multipliers of each other. All right. So 3 different ways to calculate it, and you can do any of them when you calculate this out on the first part of the lab. All right, let's see, where are we here? I think we're progressing pretty well. Okay, so the next topic here is kriging. So kriging is sometimes called geostatistical interpolation. So here, and it does build on the concepts. It's a good thing. It's a good thing to call it that. It creates a predicted value that depends on two factors. So one of them we call the trend. We kind of talked about what trend is. Okay? So kriging can include a trend. It doesn't have to actually, but it can include a trend. And elements of variability, random variability, spatial autocorrelation. In other words, how much do nearby points influence a value? This could be kind of thought of like being able to dynamically change the search radius, or having ArcGIS, or the math that's inside of ArcGIS. The kriging interpolator basically helps us determine what that search radius should be and how much influence nearby points should have in creating the output point. Okay, so that's the elements of variability aspect. So, so some examples of a trend and also local variability are these. If we were traveling up to a mountain peak, top of a mountain, we wouldn't always be going up, but in general we would be going up. And so there is a trend, and there are some elements of variability. The stock market also is always, well, it is mostly, trending upward over time. I mean, there are big peaks and values, but if you look at the stock market, since the stock market was created, it's gone up. I mean, some of that is just inflation and things get more expensive. But in general, it goes up, but there are plenty of ups and downs. So kriging takes into account both of these. It's actually really similar to IDW in that it weights those surrounding values to derive a prediction for an unmeasured location. So it's still looking at nearby values, and it can look at the entire overall trend. In other words, let's go back to here. So see how this influences these 3 points? This value right here is influenced by those 3 points. But the only thing that allows it to be influenced is those 3 points, right? This point, and this point are the only thing that has any influence on that value, that raster. But what if there was already a general trend in all of the data going up in this direction, right? What kriging allows to happen is to use these 3 nearby points as one decider, but in another decider, it also is looking at the overall trend. And so it might pull this value up a little bit because the overall trend is going up. There is an overall trend underneath. So it allows you to look at both of those aspects together. So it's oftentimes a very good interpolator. When people tested it, it does better than IDW if there's a trend around. I mean, if there's not a trend though, or if it's impossible to predict the trend, it doesn't do much better. Or can you actually even do worse? But anyway, those are the concepts behind this. Further, it can help you decide what this local area should be, how big that should be, by examining the autocorrelation. So it can say, okay, well, the nearest, the points within 10 meters are very good at helping me predict my value. Once I go beyond 10 meters, there's very little useful information. So only the nearest 10 points in this data set are useful. So the general formula for both IDW and this one is formed as the weighted sum of the data. But the weights are calculated in kriging much more complex, and it's using the trend, it's using the distance. So IDW depends solely on the distance prediction value. The Kriging method, the weights are based not only on the distance between the measured points and the predicted location, but also the overall spatial arrangement of the measured points. So it's really both a global, or it can be, you can tell it not to be, but it can be both a global interpolator and a local interpolator. It's accounting for both sets of information. Okay, so it involves usually a little bit more familiarity with your data. So you have to actually explore your data to effectively use Kriging. Make a prediction. The 2 tasks are necessary. You have to uncover the spatial dependency rules and then make the predictions, which is the interpolation part of it. And really, with any of the methods, you should do some experimenting. You should run it through and say, does that even look right? Anyway, but so the process itself, it actually is doing as a 2-step process. One of the things that it does is it creates variograms. A variogram is basically a model of the spatial dependence, the autocorrelation. It basically tells you, it shows you through a diagram that we'll talk about in a second, what the spatial autocorrelation looks like and how much spatial autocorrelation there is. So basically, it uses the data twice. We kind of covered in those 2 ways in which it does use the data. Should have shown this slide before, I think, maybe 2 slides ago, with the stock market or going up a mountain. Here's the variability, here's the trend. Okay. So things close together in space tend to be more alike than things that are far apart. Okay. So this semi-variogram is the diagram that is going to be used to calculate how big that search radius is going to be. And so the semi-variogram is defined by a distance. So you have to initially give it a distance and then kind of experiment and see how much spatial autocorrelation is being created at various distances. So you give it a distance, and it looks at the variability between that distance all over the map. So it goes through and finds, okay, if you specified a distance of 5 meters, how much variability are there between points that are on average of 5 meters apart? So it calculates the differences between those known values, those paired locations, between different values on the map. Okay. So basically, if these were all your original points, it calculates the distance and the difference between all the points in the map. Okay. And then it plots them out. And distance is one axis, and the variance, in other words, the variability, the difference in values, is the other axis. That's why it's called the semi-variogram. And then it looks for trends in the overall data. There are different ways you can specify the trend. The trend could be a local trend. The trend could be a completely global trend. Okay. All right, so the average error is going to be 0. In other words, for the trend, you're going to have just as many highs and lows. I mean, that kind of makes sense. Of trying to minimize the residuals, the differences there. The autocorrelation is purely spatial. It depends only on a distance and not on any other property, such as a position. So these are the assumptions. There are tests for this, but we're well, when we get to this part of the lab, we'll talk a little bit more about this. Okay, but this is pretty easy, straightforward to explain now. So the semi-variogram that I showed you before, which is distance on one axis and variability on the other. What's going to happen in almost every case is that variability is going to increase as distance increases. Because as you get further away, there can be more weird points. Close together, the variability is not going to be very high. Especially like if you think about temperature or precipitation. The temperature here is almost the same as the temperature here. But as they get further away, that way the temperatures all may be higher, and that way they may be lower. It's going to be harder and harder to tell the difference. So that semi-variogram, when I reach a distance, if I go out, let's go back to here. If I go out to some point, there's so much variability out here that really there's no more spatial autocorrelation. The point at which that occurs, and the computer uses math to figure this out, but it's called the SIL, the semivariance value at which no more spatial dependence exists, no more autocorrelation. Okay? The range is the distance to the SIL. So the SIL is the value on the y-axis, the range is the value on the x-axis. And then the nugget is the variation of measurement errors combined with spatial variation. The nugget's not as important. Okay? The SIL and the range, we'll show them here. Okay. The nugget usually corresponds to how close your closest points are, because really you can't measure semivariance closer than you have measured values to each other. That's the nugget here. But anyway, the SIL is this distance. So the SIL is from here. The SIL is from here to here. So it's the semivariance value which indicates that there's a plateau. The range is this distance. This distance, what it represents, is the extent of useful information for calculating an unknown value. So this is the candidate, the best candidate for your search radius distance. So that's why the range is useful. It's telling you that if you create a search distance beyond this, there's no point of doing that because there's no autocorrelation, there's no predictive value for a point outside that's beyond that distance. So here is the kind of like, this line is like the trend through the data. This would be the actual data. The points are, the line is the line is the trend again. This is what it actually looks like in ArcGIS. So in ArcGIS, it looks like this. This is the trend through the data. And where I can't tell exactly where this breaks off. Oh, but it says what the SIL. It says what the SIL is. Where's the range? The range right there. So the range is, this is times 10, so it's 7.5. So it looks like it's about right there is what it's calculated the range to be for that particular data. Now, there are a ton of different semi-variogram models. That's how it's calculating the semi-variogram. Is it calculating it based on nearby values in a circle, spherical? There's lots of different things. Okay? I don't even know exactly what all of these do, okay? But they're different functions that are fit through the circle. And so you can experiment a little bit with these, but I usually leave this on circular or spherical. Okay, so the important thing is the SIL and the range. They tell us about the autocorrelation of the data. If we have a noisy semi-variogram, then there's really not as much point to doing kriging. Okay. If the range is large, then we have lots of long-range variation. If it's small, then the majority is short range. And so if it's large, we can use a larger search radius in our interpolation. If it's small, we're going to use smaller range over short distances. So that's what that says. These are a few different approaches to modeling the semivariogram. So this is what this choices are. There's more choices here than there are here, but if you choose spherical, it will choose this model that goes up and creates a bend for the sill. If you choose exponential, it'll try to fit a more steady arc. If you try to choose linear, it'll go up in a line. If you try to choose Gaussian, which is a normal distribution, it'll look like that. It'll model it differently. So now that's actually the function part. I don't know as much about that, but there are different types of kriging. So even before you got to this screen, you could choose between a few different types of kriging that we're going to talk about here in a second. So the first one here is ordinary kriging. Ordinary kriging actually assumes that there's not any trend in the data. So it's more like IDW, except for you're allowing it to help you choose the search radius. That's how ordinary kriging works. So if you know there's not a trend in your data, or if you're unsure of the trend of the data, ordinary kriging is the one to choose for the process. So here's an example of running ordinary kriging using a spherical function, which means it bends up slowly. Here's the range that it shows. And then this is the model of the search radius and the points that it's using to consider inside of that radius. Okay. One of the things that's really neat about one reason to choose ordinary kriging over IDW is this graph. So I told you way back at the beginning of the lecture, or towards the beginning of the lecture, I said that it's important to hold out some of your points so that you can use them to verify how accurate the interpolator is. Right? Remember that? So one of the things that kriging will do, even if you choose ordinary kriging, which is very similar to IDW except for it shows the radius for you, is that it will create this graph for you, or this set of information, I should say, this data for you. And what it does is it gives you the root mean squared error, it gives you the average standard error, and you can use these statistics, particularly the RMSE, to figure out how far off you are. And the way that it works is through a process called cross-validation. It actually interpolates your surface for you hundreds of times. So what it does is go through and it holds out, 5 or 6, whatever you say. It holds out a subset of your points, interpolates the surface, calculates the RMSE, then does it again with a different 5 points and a different 5 points and a different 5 points. It's very robust, and it can create an average error. So that's very helpful for figuring out how far off you are. So what you can do is keep hitting back and change some of the parameters and go forward and see if your errors can go down in a particular surface. So you want to get a root mean standardized error near 1. So that's what this one is. Root mean squared error is in whatever units your z value is in. Root mean squared error standardized is just on a scale it's standardized so that you're trying to shoot for a value 1 or lower. All right, so this is an example of ordinary kriging on the data. So it's fairly smoothing. The other nice thing about kriging, besides producing that chart that I just showed you, is that you can ask it to produce an estimate of the error. And so this is a spatial estimate of how far off the points were when they were taken out of the model and put back in. So it can be used as a way to express confidence in the surface at a particular location. It's something that you don't necessarily get with the other methods that we talked about. Okay? So this is standard error. So in the white areas, there's less error. In fact, these are the values that we expect it to be within those values. And the standard error is, if the error is normally distributed, then we would expect the value to fall within that. That's one standard deviation. So we would expect it to fall within there about 68% of the time. It's going to fall within that value. So it's one standard deviation. If we want to come up with a 95% confidence interval, which is 1.7 something, I forgot what the z value is for 3 standard deviations. Anyway, it's something in there. You multiply this value, you multiply the values by that number, and then you could get 2 standard deviations or 3 standard deviations out. And you can do that with any of the krigings. So now we're moving on to simple kriging. Simple kriging is very similar to ordinary kriging, except for you know that there's an overall mean. Basically, there's not really a trend, but you know what the overall value should be. And that doesn't mean you know it, but you could say, I'm going to use simple kriging and assume that the mean of all these values is the average value for the surface. So, in other words, what you're saying is these points represent a true sample of a surface. Because, back in statistics, if you took a statistics class ever, you should have learned that if I take a sample of my values of a population, and it's a true representative sample, the sample mean should be very close to the mean of the population. And so if your data can support that connection, then you can use simple kriging, because it will figure out the mean for you and assume that that mean should be the average value after the interpolated surface is done. So ordinary kriging, the first one, what you're saying is there's no trend, and this data may not be representative of the overall surface. In other words, like for example, if you did elevation, but there's some big pits or spikes in your data, and you didn't even bother sampling in those areas, then you should probably use ordinary kriging. You can use simple kriging, though, in cases where your data matches or your data is a true sample of the data. So here you could get the same type of outputs. We've got almost the same standardized error. Here's simple kriging. It doesn't look much different than ordinary kriging in this case. Here's the standard error. The standard error is a little bit more detailed, okay? But it's actually wider. Not sure exactly why. 248. 264 to 280 is the lowest. Well, actually, let's look at the total range. 248 to 395. That's actually better. No. So the overall standard error is lower, which is what I expected. Sorry. I was just looking at the individual class breaks. But see how the standard error here is lower than it is here. There's a much higher range in standard errors because of the assumption that the mean value isn't known. I'm going to skip disjunctive kriging and move on to co-kriging for time. So co-kriging is kriging with more than one variable. So it actually not only looks at trends, but how one surface trends with another surface. So if you might look at, let's say, temperature and pollution or elevation and pollution together. You're still trying to predict only one variable, temperature or pollution. So there's still one predictor variable, and then there's a, sorry, I'm forgetting my terms, but there's still one variable that is doing the predicting of another variable. So there's a predictor and a response variable. But it's called co-kriging, and comes up with a different trend for each one. And it looks at the autocorrelation between the two, which is sometimes referred to as cross-correlation. So anytime you have two variables that you think might be related, you can use co-kriging, and it will use the trend of one of the variables to predict the other variable. So these are some of the basic trade-offs. There's a lot of choices in kriging. These are some of the basic trade-offs that you should understand now. Is that you can specify whether there should be a trend or no trend. That's universal versus ordinary. Universal kriging, trend, no trend, ordinary kriging. If trend, what type of trend? You get to choose the trend, whether it's first order, second order, third order, fourth order, polynomial. All right, then you choose the autocorrelation model. How many points to consider? Okay, it comes up with some recommendations, but you can fiddle with that. That's what it does with the semi-variogram. You get to choose whether or not there's a directionality. In other words, like if you were in Kentucky someplace, or maybe I shouldn't, I don't know if I'm picking on Kentucky, but you know, the Appalachian Mountains, they go like this. And so it might be that there's different type of autocorrelation one way than the other direction. So you can actually specify that. Let's see if I can go back here far enough. Did I like skip over? Universal kriging is the one that assumes a trend. Did I skip over this? I don't remember saying this.
Universal probability.
How did I skip over it all? Maybe when I went back and forth, I messed up. I'm sorry. I thought it was still coming up. Okay. So here is where you can specify the shape. You can specify the angle, and then the semi-major and the semi-minor axes right here. If you click this on, you can basically shrink one of these and increase one of these. So as it's going through and examining, it will look at more one direction than another. So you could go east, west, north, south. That's the angle, and then the axes are this way. So you can play with that. You know, if you see a trend going up and down in your data, you play with that and see if it produces a better one. Okay, so I messed up. I did talk about simple, right? I did not talk about universal. So universal, most of these are pretty much the same, except for with universal, you're saying there's a trend in your data. And you have the ability to specify what that trend is. You know, it's slowly increasing. Is it increasing on one axis, two axes? That's where you specify what the power of the polynomial is. So that's universal kriging. We do get a lower RMSE, a standardized RMSE there. Just choosing the defaults for universal kriging, indicating that there's probably some trend in the data. Now, when you start using universal kriging, sometimes you'll see this kind of stuff. And so what that's done is, because it's considering a trend and it's considering local data, you sometimes get these funny things, particularly on the edge of your data set, because it's jumping between what it should prioritize in the model. See See how that kind of looks disjointed down there? That's from it, but it looks fine up here. So particularly on the edges of your data sets with universal kriging, you'll see some of this type of thing, and it's not as pleasant, but that doesn't mean that it's not as accurate. In fact, as a measure of accuracy using cross-validation, it is higher. But the overall standard error is higher. But my guess is, look, that's probably has to do with this very edge of the data set. The rest of this is pretty low. So if we shave, probably because the trend isn't holding up really well. So the way you interpret this, remember when we did that we showed the trend of this data, and we showed it as a first order polynomial, it was just going up, right? When we showed it as a second polynomial, it went up and back down. And so what this is saying is we used a first order polynomial back here. We used a first order polynomial in the data set. Okay? And so what this is saying is that our predictions are pretty off up here. That's where they're the most off. And they're probably the most off because we're relying on that first order trend. Maybe if we switch to a second order trend, well, definitely if we switch to a second order trend, these would go way back down and would be better overall. But really, they're only in that very corner of our data set. Okay, indicator kriging. I do want to talk about indicator kriging. So indicator kriging is basically the same as ordinary kriging, except for it is really trying to only predict whether it's above or below a certain threshold. So it can be useful, like you might run indicator kriging if you were trying to do pollution and you wanted to say, is the value probably going to be above a certain point? These are the areas that need to be alarmed or notified. So indicator kriging just produces ones and zeros. Is it above or below a specified value? You could actually create this from the other map, but it shows up as an option. All right, probability kriging is similar, so it kind of builds on indicator kriging, but probability kriging looks at the probability of a value being above or below a certain threshold. So it's based on the standard error, but it's based on the standard error for actually, I think you can choose. I'm pretty sure you can choose this for any of the kriging types, but this is definitely showing a simple kriging with just a flat trend or no trend, a flat mean. So this is probability kriging. So these values represent the probability of a certain value exceeding of the value exceeding. So instead of showing you the actual value, you say, okay, well, this value is almost for sure above a certain threshold, whereas these values we're less confident they're above a certain threshold. There's the standard error, and like I said, we're going to skip disjunctive kriging. Did co-kriging now. These are the things that you should. All these have defaults. This has a default of being circular. This has a default of being spherical. This has a default value that it just chooses. I don't know what it is, but it does definitely have a default value. But you can modify these and see if your standard error goes down or changes. So this is the kind of workflow. Now, kriging is often done. Kriging can be done independent in spatial analysis, but there is a separate separate extension. That's the word I'm looking for. There's a separate extension that will allow you to create these reports. So I'm using, in this slideshow, I'm using geostatistical analysis to create these reports. So you won't get those reports unless you use geostatistical analysis by default. You could do them on your own, but they would take a lot of effort. Okay, so this is the general workflow here. You get the data, you represent the data. In other words, you show the data on the screen, you explore it, you run geostatistical analysis, and if you can fit a model, you can change some of the parameters. You can compare the models, meaning that you look at the output and see which one's creating the best set of estimators. So it's one reason that it's effective. And the other reason that it's kind of neat is that since it's an interactive process, it's creating surfaces that aren't actually rasters on disk until you tell them to be. So that's another thing to pay attention to. So it's going to create things that look like rasters, but until you actually right-click and say export and save it as a raster. So even these data sets that I'm showing here, well, actually these have been converted to raster. Let's see. I don't think I showed any of the. So anyway, they show up in your table of contents, but they aren't done yet.
That with all the interpolation methods?
No, that's just with, well, even with, here, I'll show it on here because it'll be a little bit easier to explain. So in here, in Spatial Analyst tools, there's an interpolation toolbar. Anything you run here, IDW, creating, natural neighbor, that's the one we talked about, what I call piece and polygons, trend, splines with barriers, any of these that you run in here, they don't have that wizard associated with it, and the output is a raster that's already on disk. That's that. That's spatial analysis. All right. Geostatistical is up here, and if you actually, I don't know exactly where the tool is. I always interact with it through the toolbar. It's a little bit more straightforward, and that's what the lab has you do. So geostatistical analyst, when you say explore data or geostatistical wizard, you're going to have a point data set in there, which we cover in the lab. So I'm going to take this point data set, export this out to a shapefile. It's because I didn't assign a coordinate system. The data you're going to actually use for this lab works, but I haven't assigned. So you hit Geostatistical Wizard, you follow the steps through. We'll cover this when we get to the lab. And it produces a virtual raster that's only there on your screen. Okay? So that's this Geostatistical Wizard. It's the second part of the lab. The first part of the lab, you're going to be using the spatial analyst tools down here. And you're going to be doing IDW kriging. Now with kriging, you can still output the variance and prediction raster, which can be used to derive the standard error data set. So you can still output it here, but you won't get to see the report that we talked about before unless you do the geostatistical wizard. Which this data I didn't assign a projection to, so it won't flow, but the lab will work. It just needs to know what units are in. Okay, so these are several of the additional kriging output advantages. So in addition to just producing the prediction, you can also get the standard error, the quantiles, and the probability maps. So the quantiles would just be, the 10%, the 20%, whatever you wanted to specify. Probability maps are basically that's probability kriging. That's how it's done. All right. So the last few slides here are just some examples, and you're going to be doing some of this in the lab here. So here is a prediction map that was based on ordinary kriging. So this prediction map means that the values in the output raster represent the predicted value, similar to just a plain old interpolation. So the values represent, in this case, some measure of pollution. Every value here in the raster represents that value. So here's the standard error map. In this case, the values, each value in the raster is the prediction of how well the predicted value, well, how close the predicted value is, or how confident you are the predicted value is close to the actual value. So up here, you have a lower confidence, so the standard error is higher. Probably because there's not very many points there. That's one reason for it. The other reason for it is that the points don't really fit the trend very well that we saw earlier. That's another reason. So that's the standard error map. So it gives you an idea of how well your predictions are, how good your predictions are. Sorry. All right, and then here's the same prediction map. So this map and this map are the same, but this is the 95% quantile map. In other words, we are 95% confident that the true value is that value or lower. So if you were gonna if your decision was, if this represented pollution, in fact, this may represent, there's lots of fires in California right now. You ever hear of that? Okay, so let's say that you run a high school and they're gonna have a football game this weekend, and they've told you that if the amount of pollution is higher than this amount, you're going to do permanent damage to the football players that are out there playing in the middle of this fire, right? And so you might use a map like this for all the high schools in your area and say, okay, well, if they fall in this 95% quantile, we're pretty sure that they're not going to get hurt. You might actually want to go to the 99th quantile, right, if you're talking about kids and their safety, but you get the example of why that could be useful. So we're 95% confident that the true value is either that or lower. You could look at this side and say it's either that or higher, okay, but we're talking about this one in this case. You can specify those. And really a probability map is just the same thing, but we're looking everywhere at any value that you want. How certain am I that the true value is above or below some threshold value? That's a probability map. Here we're specifying a threshold, and we're getting a probability. Here we're getting a 95% quantile map. All right. So for the lab, you're going to produce a diagram kind of like this. So we're going to look at different interpolation methods, and we're going to create a diagram like this. So actually, why don't I wait until we get to the lab? We'll use this as an example. Let's see, what time is it? Yeah, 3:02. That's good. Let's take a 15-minute break. Let's go a little longer than 15 minutes. We'll come back at 3:20, and we'll talk about the lab for today, and then that will be good. I'm going to stop it.